All right, let's go into a little more detail about tip compensation on a turning tool. Now, you ask yourself probably, why would you even need to use this on a turning tool? And you don't really, with modern cam software, you can get by without it. In fact, in the last video I made on this subject, there was quite a few comments that said that, oh, we don't even do that. We just let the cam software figure it all out. And you can do that, and it does work. But you kind of have to have a computer right next to the machine, or well, you don't have to, but you'd have to go back and forth reprocessing code if you had to make adjustments. So in the days before cam software, or cam software that couldn't do this kind of stuff, you had to kind of trig out everything when you did turning cycles. So let me just draw a simple turning thing like this. Let's just say you're turning the face and a chamfer and down the OD. Okay, now if you were going to do this and you had to figure everything out manually, you would have to think about where your tool's going to end up to cut this in the right place, the chamfer. Everything that's perpendicular and parallel to the lathe axis, it's going to cut fine the way you touch off lathe tools, but these angles, anything that's a radius or an angle, it's not going to cut in exactly the same place. You'd have to figure out the different places where it's going to cut because of the tip radius. Let me draw let me draw right here. I'll just kind of project this out. If we imagine this, and we imagine this big tip radius right here of the tool, you know, this could be any shaped tool you want. That's the tip radius of the insert. Now, when you touch a tool off, of course, you're going to take some kind of facing cut. You're going to set that Z0, and then you're going to take a cut down this OD and mic it, and you're going to set that X0 if you're doing it manually. If you're doing it on a touch probe, it's the same thing. Tool setter, you're going to touch this, and it's going to offset that, and you're going to touch this, and it's going to offset these two faces of the insert, which in reality makes that offset of your tool right there. So you can see, if you just program this path manually to the actual shape of the part, we go down here, and the insert would actually be cutting back here until it got up to this diameter, and then it would cut in the right place again. So this is the reason you want to use a compensated tool path, is it would bring that radius of that insert down to this shape, whatever this shape is, if it's a radius or a chamfer or anything. And you know, down here you'd have some kind of lead out movement. Generally for this kind of thing, I would put radiuses in these corners and lead in with an arc, and then out and go down my contour and lead out with an arc and out. So this would be the G. In this case, it's on the right hand side. I think, yeah, you're on the right hand side of the line, the contour. So this is a G42. So you have a G42 on this line and G40 on the exiting line here, and these would have to be, or should be at least, the radius of the tool or larger here. So this would go around the contour, and you could program the actual shape of the part. So in the days before we used CAM software a lot, and we did this all manually, we could program the actual shape of the part and use tip comp to go around it for the finish cut. And for the roughing cycle, you could use some kind of a canned roughing cycle on the lathe, and you could just rough this, and it would leave stock on these chamfers and stuff, but it really didn't matter that much. You could just cut it with tip comp around here, and it would finish it to size. And if you had close tolerances on these chamfers or radiuses, if you had a radius anywhere, you could adjust that by adjusting the radius of your turning insert that you were finished cutting it with. So that's kind of what we used to do with it a long time ago, but it still has its uses today for various things, like I explained in the first video about the OD groove, where you're not quite breaking these corners the way you want. You can increase the radius size. So increasing the radius cuts more into the part. As you could obviously see, if this radius was bigger, it would cut more into the part, and decreasing it would stand off the part all the way to the sharp corner here, would follow the line here, but it would be cutting way back here, of course. So that kind of explains a little bit of why we used to use tip comp on a lathe. But it acts differently because of the way you touch the tools off on a lathe. So when you see a lathe manual, if you look in the lathe manual, the programming manual probably would have this. You'll see this diagram, and it shows these directions of touching a tool off. Now you can touch a tool off in the center, just like this one shows here that are circled. But if you do that, if you touched off the tool either here with your probe or cut something or whatever, however you did it, you would have to adjust the offset by the radius of the tool in both Z and X. If you use this one, which is a 0 or a 9 on the offset page, I'll have to show you where you enter those in on the offset page. On the Mazak, it's a little bit weird how you do it on the Mazatrol, I should say. On other machines, there's an entry right on the offset page for you'll have a radius entry, and then you'll have probably what they call a direction. And this is where you would put one of these numbers in it. If you're using tip radius compensation in your program, you need to do it this way. So these are the normal directions, and you could see that the way you touch a tool off, you would touch it off either on your tool setter, or you would take a cut in the Z and you would set that offset, then you would take a cut in X and mic the diameter and set that offset here. And this is the normal turning directions for OD turning, ID back turning, and an OD back turning. And these are the numbers that you would set in your offset page. For straight in offsets like these, you would set these numbers, and you'd have to touch the tool off on the end of the insert, and then you'd have to set your offset such that it was on the center of the radius. On these, kind of like half of what the 9 or 0 is. So it would be centered, but on the end. And these are handy if you're taking a finished cut like I drew here, that like an API or seal ring groove, where you can come in here and you can go around the actual shape of the part with this offset all in one cut, as one finished cut, with using a number 7 if you're on the outside face here. Or if you're turning maybe a pulley with a bunch of V grooves in it, you might want to use this number 8 on your tool. But you would have to be careful to set your Z offset in by the radius of the insert. On this one, you'd have to set your X offset to the center line of the radius. Most of these tools that are made for these directions, you can kind of touch the tool out here somewhere, and you know the width of the shank, and you can set it half the width of the shank. Is the way I've done it before. If that's accurate, you'd have to check on your shank if that's accurate. So these are the numbers you set in your offset page if you're using tip radius compensation. And I've kind of explained a little bit about why you do it and why we used to use it for manual program a lot in the old days before CAM software. But you can run all your program without using tip comp, and say you set in your CAM software, you set your OD tool to the tip here, then you can process it and it'll work fine, and you can do that. The only thing is you have to make sure that you're setting this on your machine exactly the same way you set it in your CAM software. This is important, and I'll show you the CAM software in a second here, and you'll see the differences in the tool path between this setting and perhaps one of these other settings here. The CAM software doesn't, I don't know, yeah, it might have this setting as well in it. I have to see. I think it may. I think it has these 3: tip, center, and one of these, depending on the direction your tool is turning. So let's look at the CAM software for a second. All right, here we are in Esprit TNG. This is the software I use to program for the Mazak. Let's look at this cycle here, this roughing cycle, and this finish turning, and this roughing cycle, and so on, are being used just to demonstrate this. This little part here is actually the dead center thing I used for that needle video I did a few videos ago, and I just added this undercut, and I also added an OD groove here which I have suppressed right now. But let's just look. Let's just go look at the tool definition and see where the tool's defined. So this tool right now is defined on the tip. Let's just change it to this. See, if you're looking over here, you see this definition. I'm going to change it to the corner, they call it, here, and just say OK, and it'll reprocess the tool path, so you'll see this roughing cycle, how it changed. Let me actually hide the stock. So here, and you can see how, man, every time I do a video, that guy starts that grinder. I hope you can hear me okay. But you see how the roughing cycle, it put the tool very close in the Z direction, and the X is standing away a little bit because I have some stock allowance. And then I have the finished cut of that profile program with tip compensation on it. You see here how it looks. And then this one, this undercut area, you can see how it looks. See how the toolpath for the roughing cycle looks? And this is the finish cut, which is the actual shape of the part using tip compensation. There's nothing special about this. It's just a fake part, but just for the purpose of demonstrating this. So note the toolpath, the way it looks right here, for instance. Now let me change to this other direction, which is let's say the center, which, if you remember what I explained previous, this is the number 9 tip comp direction, and we'll change to that. And you see how the toolpath changed. Now it's running down the center of the radius of the insert for that one, and also for this one. See, it's offset kind of like a milling toolpath looks now for that. And then of course the finish cut is the same. Nothing changes with the finish cuts except the way the tool actually is compensated in the machine itself. Now the CAM software thinks that there's tip comp being applied to these contours, that finish contour and this one, so it's going to draw the tool path the same regardless of how I put this offset direction. So let me put it on the tool now. Let me put it to the number, well, this would be a number 7 in this case. Even though it looks like it's a number 8, it's a number 7, because you saw, well, I'll show you the tool tip. It actually shows it on the tool tip. Look at it here. Now, on the Mazak, it comes in this horizontal direction, but it's going to index the B-axis 90 degrees to actually do the turning in this case. But let's just zoom way in on the tip radius of the tool, and let me open the tool up again. Now see, that's there set on the corner. You can see, and the X is, the red arrow is the X, and it's pointing upward because the tool runs with its 90 degrees index down. In this case is why it looks that way. But anyway, the corner you can see is on the imaginary corner if you project the two edges of the tool. And if we set it to center, you see how it's in the center of the radius. And if we set it to the tip, it's over here on the tip, which is in this case, this tool is a number 7 on the tool tip direction on the offset page. You'd have to set this on a number 7. You have to touch off this tip of this tool and adjust the offset appropriately for the tip radius. And you notice how the tool path looks now. You see how here the diameter it's cutting at is the radius of the insert higher, and also this roughing path, see how it's the radius of the insert higher here, but it's closer to the face than the number 9 designation, if you will, or the center of the radius designation. See how it changes here? So if we look, let me go back to the normal setting that I normally use, which is this corner, and let me just run the simulation, and you'll see on the simulation how it looks. And then here's that undercut area that I programmed. And you see how all that looks in Now if I change the tip corner, if you will, to this one, which is a tip, you see how it changed the tool path. Let's run the simulation. And what you'll see is that the simulation looks identical to all three of these settings. So it can kind of fool you on your CAM software. If you're not paying attention, this can kind of fool you and you say, okay, I got everything turning correctly. But then when you go and you set up your machine, you find, uh-oh, it didn't cut in the right place. So you got to make sure that whatever you set on your machine, you set it the same as you set here, as I said before. You see if I change this to the now to the center of the radius, and you'll see how the toolpath changed again here, that toolpath and this toolpath, but the compensated toolpath is in the same place. So if we run this simulation again, we'll see that it looks identical. So you can kind of get fooled here with the CAM software and you think everything is good and you don't pay attention to your settings, is what I'm trying to impress upon you here. And the way you offset the tool on the machine is going to be different for every one of those different settings there. If I suppress this, we can kind of see how this and we unsuppress the grooving cycle and we run it, you can kind of see how it works here as far as the, well, let me start at the grooving cycle here. There's different ways it can rough the groove. I just got a kind of a zigzag path on this roughing, and then there's the finish cut on the front side. The tool's going away here, but in reality it doesn't have to move back that far, but the CAM software moves it back to a tool change position. So that's the roughing cycle for the groove. This roughing cycle on this is something that's kind of nice with CAM softwares, is you can select all different kinds of roughing cycles for grooves. You know, like you could even select this one, which is, they call a profit roughing cycle, which it's kind of like a trochoidal milling cycle but turning, if you will. So you could rough that way. So there's all different kinds of cycles. And like I said, if these corners didn't break on the finish cuts the way you wanted for some reason, you could adjust the tip radius in your tool, because I'm actually using a compensated tool path for each one of those finish cuts. This is the back side of the groove, if you will, the front offset on the tool, and this is the rear offset on the grooving tool. So you run two different offsets on the same tool for grooving to do this kind of thing. So that's that kind of roughing cycle. Or you can select a zigzag thing like this, and it zigzags down like that. It's just different ways you can rough grooves using the CAM software. So normally, if you're just using like a canned grooving cycle in the machine's control, you're pretty much going to have to use this straight in peck cycle, which is well, it might be multiple plunges, and then you can set a peck depth and everything here. And that's the way it would look. So you can do different cycles with the CAM software, which is nice. And also you can do that with roughing on OD or this undercut and everything else too on the CAM software. So that's looking at the CAM software. And the only thing I'm really trying to impress upon you is to have your settings the same. And you can use tip comp, because that's what I'm doing here on these cycles with the CAM software as well. Notice how, because I've grooved out this groove, that the stock on this CAM software, it knows that stock's removed by the grooving cycle. So the actual roughing cycle for this undercut takes that into account. It's kind of interesting, isn't it? So it actually if I show you the stock definition, this is the stock from the finished groove, and now it takes that into account for the roughing tool. In fact, let's just run it for the heck of it. See how it knows that that stock's been removed by the grooving tool? So those are the kind of things you can do with the CAM software that you really can't do, well, you could do it, I guess, but it'd be difficult to manually program that way. So anyway, I just want to show you the difference in the selecting different tip directions in your CAM software. And like I said, this needs to coincide with the way you actually set the machine up. Or if you're programming for somebody but not running the machine, you need to tell them this is the way you did it, because they could make a mistake and screw up the first part if they didn't know this. This is the normal one I use as a corner for most everything. All right, here we are at the Mesotrol on my Integrex, and let's go to the tool data pages here. And first, let me just toggle over to this, and we'll go down to these settings. So this is the way you set offsets on the Mazak. Let me see if I can get rid of some of that glare. Okay, you set the B direction and the A direction. So this is the spindle, and you set the length and the distance out from center line on this. And this is the way you set a milling tool, of course, just the length. And then you would put the diameter in the offset. And these are the A dimension, it's on highlighted there, and then the B dimension. And then this will be the tip radius of the tool. And here's your normal like wear offsets down here. Now, this number, now it took me a while to figure this out, but this little number right here is referring back to another offset on this machine. Actually, it's not the direction. I thought at first it was the direction of tip comp, but it's not that. It's referring back to another offset. So if we go back to this offset page, see we have two different offsets on the Mazak. You can run with what they call the Mesotrol tool definition, which is what this is, or you can run just a regular offset, which is this is the offset. So for that first tool, I'd be using this, but see, you can only run like one offset per tool. Of course, there's many pages of these, so you could run tool 1, and then you could run tool 100 for the same tool 1, or you could do anything you want here, actually, if you call the offsets in your program up a certain way. But the only thing I use these for is right over here. So you see we got X, Y, Z for the offsets, and then we've got nose radius, and then wear comp in X, Y, and Z. There's a Y on this machine because it has a Y axis for turning tools. And then there's what they call a direction over here. I don't know if you can see that. Let me get closer maybe. You can see it says here's the nose radius and here's the direction. Now, get the camera adjusted here. The only thing I use these offsets for is for these directions. And you notice I have offset 1 set for 1, 2, 3, all the way down to 9. So the offset on the other offset page, if we go back to the tool data page, we move out here a little bit, that's what this number on the Mesotrol is referring to. It's going back to that offset, and it's getting whatever's in that offset. Now, the only thing I set on that offset is the direction of the tip comp. So we go back here, which is the only thing I set on the first 9 offsets here. Now, you could use these offsets, like I said before, to run everything in the machine if you wanted to, which I guess is the intention, is to run what they call EIA programs with this maybe. And there's many pages of these. I don't know how many. It goes up to 128 of them, it looks like. Yeah, 128. But I don't use these for anything but to set this direction, because on the tool data for the Mesotrol, there is no direction setting because Mesotrol does not use it. They compensate everything for the tip radius in all directions, it automatically calculates that, so they don't need it. But if you run this offset page in an EIA program and on a turning tool that you're using tip compensation for, you have to be able to set a direction. And the only way I could figure out how to make this do it, and believe me, it took me like a whole day to figure this out, is to set these directions on these first 9 offsets and then refer back to whatever offset I want, you know, for the direction I want, which coincidentally I just set it, you know, for the first 9 numbers on the first 9 offsets. So I just set this now to the offset direction for the tip comp, and it works. Don't ask me why Mazak did that, but you know, that's what they did. Who can say? On the actual Mazotrol, you can see they have all these various angles of the tool, you know, the nose angle, the cut angle, the edge angle, and all this stuff here. And so you can set all that, and it automatically compensates for the tool in the direction you're turning, and the cut angles of the insert, and the nose radius, and the edge angle would be, you know, this the actual cutting angle of the insert, like an 80-degree diamond or a 35. I don't set these things typically for the stuff I do, because I run EIA programs or G-code programs, and none of that stuff even matters. This setting here on the Mazak tool setup for a lathe tool is the way it orients and clamps the spindle in the milling spindle on this machine, which it can do it like this, or you can do, I don't know if you can see this down here. Maybe you can. Down here, you can do standard or reverse, which is like this one. It happens to be reverse, which is 180, or standard at 0. Or if you select this flash tool angle, you can index and clamp the tool every 15 degrees, which is necessary for some tools. And I did use that when on my anvil program, I defined the broaching tool as a lathe tool, and I indexed it every 90 degrees to do all 4 corners of the square Hardy hole. So anyway, that's kind of showing how the Mazotrol actually finds this number, because it isn't necessary for their control to even specify this number, but for an EIA program, it is necessary, and that's how I do it. I just use the first 9 offsets on this offset page, and this number refers back to that offset and collects whatever data you have over here, and the only data I have set is the direction data on those offsets. So I assume, although I've never tried it, that it would apply these datas on top of the Mazotrol data, possibly, but I've never tried that, like the wear offsets and the various things. So that's how the Mazotrol does it. But a standard controls page looks more like this does here, with the you know, you would have your various X, Y, and Z offset depending on what your machine's, the axes of your machine, and then the radius, and then the wear offsets, and the nose wear offset, radius offset, and then the direction of compensation. That's kind of a typical way a lot of lathes have their offset page, although they probably show it more like this, you know, a little bit nicer graphics, but that's the basic entries. So like I said, the Mazotrol, you got to set this number, and all they say is number here. And I don't know, they don't really explain this in their manual very well, if they do at all. I couldn't find it, and it took me quite a while to figure out this, how to set the nose radius direction in an EIA program. So anyway, that's a little thing about the Mazak offset page and how it works.